Our goal today is to look some more at how this key concept of integration, that when we integrate a rate, we always get net change. That's a major, major concept you really need to know. And we've seen it time and again with velocity and its relationship to net position, or I guess the word is net displacement, how velocity can be thought of as the rate of change in position, and when we integrate it, we can come up with a net displacement or a total change in the position. But velocity is not the only way that we can look at this. So in this example, we're going to look at a different kind of rate, and we're still going to use integration to get the total. This comes from the 2005 AP Calculus exam. This was calculator active, and it was on the free response. This is a typical type of question. It kind of has a name, actually. Let me read through it with you, and then I'll tell you about the name. We have a tide, water, you know, the ocean, removing sand from Sandy Point Beach at a rate that's modeled by the function r, and r is given by this function equation. A pumping station is adding sand to the beach at a rate that's modeled by the function s, given by this function. Both r of t and s of t have units that are cubic yards per hour. Units are always a big hint, we know that, so that's something that you should be underlining. T is measured in hours and is valid for times from 0 to 6. And we know that at time 0, the beach contains 2,500 cubic yards of sand. Now, I want to back up to tell you about this type of problem. This is what we call a rate in, rate out problem, and let me show you why. The tide is removing sand from the beach at a rate that's modeled by this function r. So r is the rate in, or the rate out, excuse me, because our sand is being removed, the rate that we're taking sand away. Now, on the other hand, we have s, and it is the rate that we are adding sand. Okay, so we're adding sand at this rate, and so this is known as a rate in. So if you think about this beach, at all moments in time, we're both adding sand with the pumping station at the same time that we're taking it away with the tide. And so we want to kind of figure out how these two rates in and rate out are going to play against each other in terms of how much sand we have on the beach. The time 0 with the 2,500 cubic yards of sand, this is going to be an initial condition. So that gives us an idea of where we might have started. So let's read the first part. How much sand will the tide remove from the beach during this 6-hour period, and indicate units of measure? So we want to know how much sand. I'm thinking like total amount of sand. And we're also talking about the removal of it. So remember, the removal rate was r of t, but we want to know the total amount of sand that was removed. So this is a specific example. This is what's the word I'm looking for? A perfect example of integration to get a net change. So on this one, I would integrate, as you might imagine, the rate that we're removing it, r of t, with respect to time. So r of t dt. And we're going to do that for the 6-hour period running from 0 to times 6. So this will be a definite integral. Now this should give us the total amount of sand that is removed from the beach over the 6-hour period. And I want you to notice, this is an AP strategy. Notice that I did not copy down the full expression for this function. I just used the name of the expression as showing my work, and that is completely valid and will save you a lot of time and possibly some errors in copying it down. Also, something you should always do when you hit a question like this is you're on your calculator active, you need to start by putting those two functions in the calculator. We've talked about this as well. So I'm going to take a moment to do that. You should be doing it with me. Okay, I got to go into y equals. Get rid of some of these. All right, let's get this in here. And we'll put in y2, I'm going to put the rate for the s function. You guys might want to use the templates. I know you like them. I'm just going to make sure I put parentheses around the denominator. So there's my s function and my r function. And while I'm at it, I better check my mode to make sure I'm in radians, and I am. So we're good to go. Okay, so I've got my functions in here. In part A, I am just looking for this definite integral, and I'm going to do that right from the home screen. So the definite integral is math 9. We want to run from 0 to 6. R of t is where I have y1. That's going to be alpha, is it F3? Nope, let me try that again. Alpha F4. There we go. Oh man, I get to start over. Okay, let's try this again. Math 9, 0 to 6. Hopefully you're doing better than me here. The y1 function with respect to our dummy variable x here. Okay, so this is our answer numerically. We're going to have this equal to 31.815 or 6. You can either round that or just truncate it. I'll go ahead and put 6. And so that's the net change, or the amount of sand that was removed in the time period, 6-hour time period. Now we have to indicate units of measure. And this one I don't think is too hard, but sometimes it's a little hard to decide what your units of measure are. So I'll remind you, your units for the function and the differentiable dt should be giving you a hint of this. So what did they tell us that the units for r of t are? Back up here, if we look, both r of t and s of t have units of cubic yards per hour. So this part of my function, of my integrand, this part is measured in cubic yards per hour. But there's also the dt part, and that dt, that differential, has a unit as well. That's the little change in time. Time here is being measured in hours, so that unit gets multiplied by this rate unit, and the hours cancel, leaving me cubic yards as my unit. You might have guessed that, but I wanted to see how it worked with the unit analysis there. So we've got 31.816 cubic yards of sand being removed in the 6-hour time period. Alrighty, that's part A. Now part B, we're going to write an expression for a new function. The new function is y of t, and this new function represents the total number of cubic yards of sand on the beach at time t. So this is the meaning of y of t, and we're just writing an expression for that. Now this takes me back to the fundamental theorem of calculus with that special way that we wrote just the other day. I am going to want to consider really 3 things. How much sand was on the beach to start, how much total got removed, and how much total got added, because those 3 things are all happening together. So y of t could be an initial value plus the amount that was added minus the amount that was removed. That's kind of the thinking in my head here. Now, would I write this on the AP exam? I might if I was needing to keep track of everything. But what they're looking for the graders is they're looking for mathematical expressions for this. So it would be y of t is equal to our initial value. How much sand did we have to start? Remember, that was our 2,500 cubic yards of sand. So 2,500 cubic yards plus the amount that was added. Now all we have is the rate that we added it. So to get the amount that we added, we're going to need to integrate. And we're going to need to integrate from time 0 up to time t, not to time 6. That's actually a pretty common mistake. We want to get this function in terms of time, not at the end of the 6 hours. So this is going to be the function variable t here. And the sand added is the s of t function. Now I can't use t here and use it here. I need a dummy variable right here. So that little s of x, that's just a dummy variable. The true variable of my function is that upper limit of integration. Okay, so seeing what we have so far, we've got the initial value. This is the total that was added up to time t. And now I'll subtract away the total that was lost up to time t. So just like we built this one, we're going to do this one from 0 to t of r of x dx. Again, x is a dummy variable. And that will give us the total amount we lost. So this is the answer for this expression. Now there is one other way that you might think to do that. You might decide to condense these 2 integrals into one integral. So another option for you would be to say y of t is equal to 2,500 plus the integral from 0 to t of s of x dx minus r of x dx. And actually, that isn't even right either. Let me try that one more time. I've got too many dx's in there without my integral. Okay, I'm going to do that here. So I meant to say it would be y of t is equal to 2,500 plus the total amount from 0 to t of S of x minus R of x. The actual dx needs to be right here to close that integral. So we're looking at the difference between the rate in and the rate out and integrating that difference to give us a total amount of sand added or lost. Okay, so you could either write what's here in red or you can put this form of it. Either way, you've got the same idea with it. Okay, moving on. Part C, we're going to find the rate at which the total amount of sand on the beach is changing at time 4. Okay, so I need to find another rate, and it needs to be the rate that the total amount of sand on the beach is changing. So do I have a function that tells me the total amount of sand on the beach? Think about that. Pause the video and tell your neighbors, what do you think? Do I have a function that gives me the total amount of sand on the beach? All right, so if you decided that, yeah, we do because we just figured it out up here in part B, you're exactly right. Y of t is the total amount of sand that's on the beach at any given time. We're going to need it at time 4. So what is this question really asking me to do? Find the rate of change in y of t at time 4. Well, that sounds to me like figure out the derivative of y at time 4. The rate of change in y at time 4. Okay, so that should be pretty easy to do. In fact, we could probably do it, a lot of it without a calculator. Think about y of t in this way. We've got expressions for it. So can we take the derivative of this? Well, sure we could. Y of t derivatized is term by term. What's the derivative of 2,500? We know that's 0. And what is the derivative of this accumulation function? Remember, that means just plug in this upper limit into the function, replace the dummy variable, so that'd be S of t. No chain rule needed here. The derivative of t is just 1. And move to this term, and its derivative is just like the derivative before it. It'd be R of t. So the amount of sand on the beach, this makes kind of common sense. The total amount on the sand on the beach, wouldn't that be changing at a rate equivalent to the rate that it came in minus the rate it went out? That would be a total rate change, or the total rate of change of the total amount. I'm not saying that very well. I hope you're understanding. Okay, so I'm going to go ahead and figure out what this is at 4. That just means I need S of 4 minus R at 4. That's something I'm going to put in the calculator, again, here from the home screen. My functions are still in y1 and y2, so this was y2 in my function. I'll go alpha f4 and grab y2. And we'll evaluate that at 4 and subtract y1, which is my removal rate, also evaluated at 4. So we are getting a rate that's negative 1.90. I'm going to call that 9, rounding it up. And we better indicate units of measure. Well, what were the units of S and the units of R that we just subtracted? Remember those units again. S and R are both units of cubic yards per hour. So when I get the difference between them, I still have cubic yards per hour. And from that, if we needed to interpret it, that means that the total amount of sand on the beach is decreasing at a rate of almost 2 cubic yards per hour at time t equals 4. All right, our last part D here, let's read through it and then see what we're going to do. For time 0, between 0 and 6, and that was a typo. You guys need to add something. They lost in the printing, it looks like they lost the or equal to. That should say or equal to. Please add that. So for the time between 0 and 6, what time t is the amount of sand on the beach a minimum? And what is the minimum value? How do we find a minimum? We're going to use the candidates test here. Okay, so our candidates for the minimum value occur when time is at endpoint. So let's make sure we use 0 and 6. But for what function? What function are we trying to minimize? Read it again. What time t is the amount of sand on the beach a minimum? So our function is the function for the amount of sand on the beach. Again, that's y of t. So we are going to need to figure out what y at 0 is for our first candidate endpoint. Also what y at 6 is. and then any critical numbers that we get. And let's go find those critical numbers. We'll just come back to this in a second. So critical numbers are where the derivative of our function is 0. So we need to figure out where y prime of t is equal to 0. Another way to do that is, remember, y prime of t is the difference between s of t and r of t. So we could also be saying we need to solve the equation where s of t minus r of t is equal to 0. That's another way you could say it. And even a further simplification, you might just need to say, where does s of t equal r of t? Just moving the r of t over. Any of those three equations will get you the point for figuring out what the candidates are. Which of those is going to be easier to solve? Well, that's kind of up to you and your comfort level with your calculator. I think for the purposes of this example, I'm going to just solve this equation. I've already got those two functions in. I'm just looking for where the rate in is equal to the rate out, which will be a critical number. So this I'll do from the graph screen. Before I graph it, let's go get a window where our time, or I guess our x min and max, runs from 0 to 6. So we'll put x min at 0 and x max at 6. I really don't know what the y min and max should be. I could think about that, I suppose. I think I'm just going to graph it and see if I can get an intersection. So mine is set at -5 to 5. I have no clue if this is going to be good or not. Let's take a peek. Okay, this is my S of t. This is the pumping station, and it's not a good curve. Something interesting is happening up there, and something interesting is happening right there too. Okay, so I am going to change my window. Let's go up a little bit higher and take a look at what happened up there. I don't think there's another intersection to find. And I'm not totally sure what's happening right there, if that's just a little touch point. But this is a clear intersection, so this is a critical number. Our x value right there is a critical number. And I am not too comfortable with what I'm seeing right here. So I'm going to ditch this idea. I am thinking that that's a critical number and that might be, but I've changed my mind. I'm going to go and figure out this function. I like finding zeros a little bit better. So let's go back and let's put in a third function. This one's going to be y prime of t, which, remember, that's s of t minus r of t. So I believe I can just do y1. Nope, let me do y2. Remember, that's s. S is y2, and subtract y1. I think I can just graph that as a function, but before I do, I'm going to go turn off these other ones. So to turn those off, you're going to need to arrow over until your cursor is on the equal sign and hit enter to turn that off, and then let me arrow up and hit enter and turn that one off. All right, so they're still in there and I can use them, but I'm only going to graph the one that is selected. So let's take a look at the graph now. This is the graph of the rate of change in the sand on the beach. Okay, so let's go ahead and find this critical number. I'll do that with calculate, finding the zeros, so calculate number 2. Let me put a left bound on it. I know it's to the, that's 4 there. 4 is to the left, so left bound I'll put 4. Right bound I'm going to put 5.5, 5.5. Just make sure that this little interval they're marking, that your 0 lives in there. Okay, so this 0 is t equals 5.117 ... And I want to store that value so that I don't lose the accuracy of that. So what I need to do is make sure it's showing on my home screen or on my graph screen. And right away, I need to quit out of this and go back to the home screen. So I'm going to do second quit. And now I'm going to store, hit store. That's the answer from the graph it's going to take for me. And I'll store this as A. Okay, so that's the same x-intercept that we found on the graph there. So we're going to let this equal A, and we'll do that on paper so we can use it. Alrighty, and let's see. Do we think that this is a 0 or not? Let's go and see if we can find one. So we'll just do second calculate. Another chance for number 2, the 0. And our left bound, you can arrow over. I'm just going to type it in. It's got 0 on the left of it, and the right of it would be 1. That's really close there. So somewhere between 0 and 1, and then a guess, just hit enter. The calculator's having a hard time finding it, and that is because it doesn't exist. There's no sign change it was looking for. So we know that that one is not a critical number, and if you're not totally sure, you could always spend some time zooming. Let's just zoom in a little bit right there. Get me closer to that point. See if we can convince ourselves. Yeah, okay, that's pretty convincing. It does not hit 0. So we have only one candidate from critical numbers, and that is this decimal value right here, which we've stored in the calculator as A. So y at, oh, you can put it in 5.117 ... or you can put in y at A, since you stored it and you told the reader of your work that that was A. You can put either one in. Okay, so now we have to just figure out what these values are, and we will have our answer. So y at 0, remember we have a function here. This is our function we got to deal with. So y at 0 is the original 2,500 plus the amount that got pumped in, and that's from 0 to 0 of s of t. What am I doing? We know y at 0. What am I doing? This is 2,500. We were told that. Don't be wasting time doing that. Okay, how about y at 6? So y at 6, this is what I should be doing. 2,500 is what we started with, plus all of the amount that got added by the pump, that's from 0 to 6, of s of t, or x. You can put it here because it's not a variable there, so I'm going to go ahead and put s of t dt, minus all of the sand that got washed away by the tide from 0 to 6, and that's from r of t dt. All right, we will calculate that in just a second. Let's go to the last one. It's the same calculation. It's still 2,500 to start, plus all the accumulation from 0 to, probably, I'm going to put A here rather than recopy that. S of t dt minus away all the washed out sand from 0 to A, integrating r of t dt. Okay. So let's just calculate those. Let's go back to the home screen. Okay, so 2,500 plus the integral from 0 to 6. This is for y2. And then subtract the integral from 0 to 6 for y1. What'd I do? It doesn't like y2. Oh, why? Why not? Is it because I turned them off, I wonder? Oh, right. I think I picked up a different calculator. I've got too many calculators here. This is so funny. Okay, well, I can probably imagine that Gabe is sitting there right now wondering if we can use this form right here instead of this double integral form right here, this condensed one. And the answer to that is yes, Gabe, you can. And I'm wishing that I had now. I feel committed to this, though, so I'm going to go ahead with what I've got. All right, let's get this done. 2,500 plus the integral from 0 to 6, y2, and the integral, subtracting the integral from 0 to 6 of y1. You guys probably already have this answer. Nobody can see that. Sorry for that glare. All right, it's a thinking. Ooh, look how close that is to 2,500. A little bit less though. So this is 2493.977. got the wrong color. And it's getting crowded. Okay, now rather than retype all that, let me just arrow up and copy paste that line in here. And I'm just gonna go and change. All I have to do is change those 6s to the other candidate, which was the 5.177 that we have stored as A. So this is gonna be to the A, or the upper limit there is A, and there's a second one back here, and that needs to be changed as well to my stored A. Okay, so let that run. 2492.369. Okay, and we wanted the minimum value. So of all of those values, the minimum is sitting right here. And we are going to justify our answer, and we're going to write, well, this is the justification, but we are going to write this in a full sentence. So at time equals 5.117, the amount of sand is a minimum value of 2492.369, and what are our units? Cubic yards. There's the work that justifies our answer. And now you can see it. There's our answer. Okay, now that was a lot of detail. Normally you would be doing this problem probably a lot faster than I was, but you would not be explaining it, and you would have the practice that you're going to get from doing your assignment. So do some AP style kind of these. And remember, you can send me a text. If you get stuck somewhere, I can probably help you. We'll figure it out. Good luck, you guys. I'll see you soon.